So let's start with the introduction. So what is the multiphase flow? If we see anything around us, it is a mixture of different fluids and solids. Like if we take a glass of water or tea, it have interaction with the air. Secondly, there has been solids that are being mixed in the tea, like sugar. And if we see the air itself, it is a mixture of different gases, solid particles like dust and the water vapor. So all of the three, like the liquid as a gas, different gases, and the solid particles are is the part of the air. So air is the best example of the multiphase fluids and solids. So any simulation or any physical when we are going to study any physical phenomena that involve more than one fluid or like liquid, gas or solids, it is being called multiphase. So there are the different types of the multiphase flow. If there are two types of phases, like gas and solid, like we want to study the pollutant or carbon particles in the exhaust gases, so it will be a mixture of gas and solid phase. And if we want to study the mixing of the ethanol with the water, for example, so it will be a liquid to liquid two phase flow. So if we want to study the mixing of the different gases like the oxygen with the carbon dioxide, so it will be a two phase gas flow. So if we want to study the all of the three uh, phases like gas phase, solid phase and liquid phase, the best example is I will take the exhaust gases again. So there is a phenomena in the exhaust gases that we call the liquefaction of the vapor that are coming from the exhaust. So there is the vaporization and the condensation phenomena, which will involve the liquid phase and the different types of exhaust gases like the carbon dioxide, oxygen and the other component. So the third one is the solid, like the carbon particle or unburned fuel. So it is the best example of the three phase flow, which involve the gas, solid and liquid. So if we talk about the fluid interaction, it can be gas or liquid. So there are two types of interactions. Some fluids are mixable with each other and some don't. Like if we take the oil and the water, we can't mix them with each other, but the ethanol is the ethanol can be mixed with the water easily. So there are two types of the fluid, miscible and non-miscible. Just one second. So for these two types of fluids, each fluid has its own physics. Like if we talk about the miscible fluids, they can form a homogeneous mixture and they does not have a distinct interface. Moreover, if we talk about the best model to visualize the miscible fluids in the Ansys Fluent, the species transport model is best for diffusion. The physics behind the mixing of two fluids is the or gases is the diffusion. So we can model the diffusion with the species transport model. So if we talk about the immiscible fluids, so here we take the free surface model. So to model the immiscible fluids in the Ansys Fluent, the most appropriate model is the VOF model, or we can also use the other models like the Eulerian approach. So the best example, if we talk about air and methane, is the miscible fluids, and if we talk about the liquids, immiscible fluids, so oil and water again is the best example, and even the water and air, where we can take two phases, like the one is air and other is the one is the gas and other is the liquid. So these are the important aspects of the miscible and immiscible fluids. And we have just to take in mind that if we want to model the miscible fluids, we have to take the species transport model. It is the best to track the diffusion. And if we want to study the free surface, the most simplest and easy model is the VOF approach, volume of fluid model in the Ansys Fluent. So there is the third one interaction is the fluid and solid interaction, like the particles of solid that are being dissolved in the water or any other liquid. One of the best example is the flow of the slurry through the pipes, or sedimentation, which is a process in which the solid particles stay at the bottom of the liquid after some time. Like if we mix the sand in the water, after some time it will suspend in the bottom of the water. So it is not miscible in the water, but or it does not dissolve in the water, but it can be suspended solid for some time, and after some time it will lay down in the bottom. So there are 5 different models for the multiphase. Primarily there are 3 models: volume of fluid, Eulerian approach, and mixture model. Discrete phase model is compiled with one of these model to study the solid interaction with the fluids. And species transport model, basically the species transport model is not primarily the multiphase flow, and does not track the different physical phenomena like the drag and lift or free surface between different fluids. It is mainly model for the diffusion of the different species into each other, and the reactions of different species with each other, like the burning of the coal particles in the combustion chamber is one of the example of species transport model. So basically these are the three these are the 3 primary models of multiphase, which is volume of fluid, Eulerian model, and mixture model. So if we talk about the volume of fluid model, in the previous versions of Ansys Fluent, we can only model the free surface, like immiscible fluids. We can model these with the volume of fluid model, but now we can also model the immiscible fluids with the VOF approach, but it is still more suitable for the free surface flows. If we talk about the interface modeling of the VOF model, we get 3 different type of interface now in the latest versions of the Ansys Fluent. So one of these modeling technique is the sharp interface modeling, in which a distinct and well defined boundary is modeled in the two different or three different fluids. It depends upon the simulation. So again, it is the best for immiscible fluids. If we talk about the other second approach in the VUF model, is the dispersed interface modeling, in which we can model the miscible fluids like mixing of ethanol with the water. It can be modeled with this approach. And the third one is like the mixing of air with the water. So in this case, if we see the practical example, some of the air particles are being trapped in the water when the air is being mixed with the or being pushed in the water. So some of the particles are being mixed with the water. So it is the combination of sharp and dispersed interface modeling. So if we talk about the Eulerian model can be used for the miscible or immiscible fluids. And in the Eulerian model, the best thing we get, we can model the advanced and complicated CFD models. Like if we see the fluidized bed reactors, so there are three phases: solid, gas and liquid. So we can easily model this type of problem with the Eulerian model in the combination of DPM model, which is we have discussed earlier, discrete phase model. So the mixture model is primarily used for the different type of fluid mixtures like the air and water, or the methane and air, and these different types of fluids. And we can study the now it is being there is a confusion about the species transport and mixture model might be like in the species transport that is also a mixture, and in the mixture model we are again studying the mixture of different fluids. But in the mixture model we can utilize different types of physics like the cavitation, boiling and condensation. But species transport model is primarily used for the reactions and diffusion of the liquids. So it is the clear difference between mixture model and species transport model. So the discrete phase model, as I have mentioned earlier, is being used to model the solid particles. It can be combined with any model like the VOF model or the mixture model, Eulerian approach, or species transport model. Like one of the example with the species transport model, if we want to model the combustion of coal particles, so we will take the coal particles as discrete phase model, and we will combine this with the species transport model and define the reaction of coal particle with the air, and the conversion of coal particle into the different gases. And in the if we see the other approaches, or might be we will discuss it later in the example section. So I have discussed about the species transport model too, that it is being used to model the transport of different species like the air. Even in the air In species transport model, we have different components of the air. It does not treat it like a single material. So it's primarily used for the reactions of different materials with each other and the transport of different species. That is the main important point regarding the species transport model. So we have to choose the appropriate model if we want to get the exact results. So there are the examples of advanced multiphase simulations. Like first of all, the dissolution is a process of mixing of solids in liquids, like dissolution of the sugar in the water or some kind of medicine in the liquid. It's called dissolution. So how we can model the it is an complicated thing. Inshallah we will try to make a tutorial which will explain it in the detail, like how we can model the dissolution in the Ansys Fluent. It is a little tricky process because dissolution process is not available by default in the Ansys Fluent. So other is the combustion of solid particles. We have discussed it already. The third is the condensation and evaporation. So you can see the application of condensation and evaporation in your daily life, like the condensation of the water around the glass of a cold water, and the cavitation. It is an other important physical phenomena that mostly occurs in the pipes and in the compressors, pumps, and if it is not being properly studied out and not considered in the design, it can cause major issues and damage to the equipment while working. So boiling is also a phenomena related to condensation and evaporation. So there are three other types of examples, like bubble column reactors, in which the gas is being injected into the liquid, slurry flows, and gas liquid droplet flows, like the spray of the perfume is the best example that you can easily understand. So in today's session, we will see two of the phenomena: simulation of the simulation of the cavitation and oil water mixing in a pipe. So these are the two different types of problems we will study out in today's session. So first of all, we will study the simulation of the cavitation, where the water is being injected into this pipe at high pressure. It is not a pipe, it is a nozzle, but we are to save the time, we will study out in the 2D instead of 3D, so we can see the work in the less time. Let's the so wait for the software to be loaded. taking more time as usual. Workbench is being loaded. Okay, so I have already run a simulation. Let's start it again. First of all, we have to import a geometry. What type of mathematical model you are using? Are you being using the rigid body or the MRF approach? My system is a little being lazy. I think the storage is being full. Okay, for MRF approach, most of the time we have to use a smaller number of time step size in comparison to the rigid body, so it is more time consuming, and also it is not accurate model as in comparison to the rigid body. So in MRF approach you should have at least, if the especially if the turbine or any other body is rotating at high speed, like you, if for every rotation there should be 270 or 300 time steps that are being suggested to get the appropriate results. So if the turbine is rotating at 1 revolution per second, so you have to divide 1 second in 300 time steps. So divide 1 by 300, you will get the appropriate time step size. So let's come back to the simulation of cavitation. So I have take, first of all, the first assumption we take in our simulation is the we have created 2D geometry of the 3D model. So we consider in all of the section, if we see in 360-degree, the flow has the same pattern. Secondly, we have cut out our section in the half, so in other half we are considering the same flow pattern. So first of all we have to create the meshing, and meshing is one of the important important part of the simulation. If the mesh is not accurate, you will never get the exact results. So my method of dividing the geometry, I take the default size, like in this case it is 2.4679 millimeters. So I want to refine it 20 times, so I will divide it by 20, so I will get the element size. So I will use this element size for this face sizing. Secondly, I want to add inflation layer at the boundary of the walls, so I can accurately model the flow near the wall. So I have choose these 3 walls, and I will use the first layer thickness as a start. So I will take 2, and I want to the first layer thickness size is 0.049. so number of layers I want to add near the wall are 20. So let's generate the meshing. In the meshing, it's being always suggested to use hexadominant meshing, and it provides better results as compared to the triangular meshing, and it saves time too. Like most of the geometries, the triangular meshing have 3 times more number of cells in comparison to the hexadominant or quadrilateral meshing. So always try to make the discretization by using the hexadominant technique instead of using the triangular meshing or tetrahedrons in case of 3D. So if the turbine have 36 rpm, so you can first of all convert it into the revolution per second and then divide it with 300. You will get your time step size. Let me take a rough mesh size so we can complete it in lesser time. So I am taking this size. And for inflation, still it is not a good number, so let's take this thing. Okay, secondly, let's decrease the number of inflation layer. So the second step is to define the boundary conditions. Inlet, outlet, and axis. Update the meshing and go to this setup section. Okay, I will show you the how to check the mesh quality in the second simulation. Okay, so the setup started. Let me open the CFD post to save the time. So once we have started the Fluent, first of all we have to define the axis metric, because we are taking the approach of having a symmetry of a circular model. So this yellow line will be considered as axis, and we are doing a steady state model and the pressure based technique. So to model the cavitation, let me first add the materials. Water liquid and water vapor. Then we will change the properties of the water vapor, density, and the viscosity is 1.26 and plus 0.6. So okay, we have selected both of the fluid materials. So now go to the multi-phase model. Choose mixture. Number of Eulerian phases are 2. Click apply. The primary phase is water and the secondary phase is the vapor. I am keeping the default diameter